Hi, everybody, and welcome to Science Talks. For those of you who are new today, Science Talks is a series of online informal talks where anyone can come and explore the latest ideas in science, research, and technology. These talks are followed by Q&As, which are designed to engage learning about recent research in science. So let's go and explore the latest ideas in research and science. Before we get going, I'll do a run through of the program so you know what to expect for this evening. We'll have a talk from an expert, and we'll get to the intro shortly. Afterwards, there's a Q&A portion where we really encourage you to ask your questions of the speaker, and you can put those in the chat, and we will bring them up in a panel session after our presenter. And then at the end, we'll do some closing remarks. We just ask of those of you here today not to turn on your video or your mic. If you have a question, you can raise your hand. And if you would like to ask it personally, use that feature. We can let you speak to our presenter. Otherwise, type your questions in the chat and we'll bring them up to our speaker. And just so you're aware, the event is recorded today and it will be shared online if there's someone you'd like to share today's presentation with afterwards. So we here have a community agreement. This is meant to be a really special conversation with an expert that we've brought here today, and we welcome a wide range of questions. We encourage a safe environment that promotes curiosity, open-mindedness, and discussion and inclusion. This is not really a space for if you have an agenda or trying to self-promote. This is to really focus in on the research that's being done and making it accessible to the community here. So before I continue on, I would like to introduce my co-host here this evening, Tiffany, who's going to do a few thank yous.
Hello, everybody. Again, welcome to Science Talks. We are very glad to have you. We want to do a special thank you to the people that originally made this possible through the City of Abbotsford, the Vancouver Foundation, and the Abbotsford Community Foundation through the Responsible Neighborhood Small Grant. Thank you so much for helping get us kick-started, and we have had an absolute pleasure of bringing all of these talks to you guys. As well, we would like to thank some of our other sponsors as well, the University of the Fraser Valley, the Abbotsford Tech District, as well as Connext, UFB Alumni Association, and TEDx Abbotsford. None of this could be possible without these amazing companies by our sides helping us the entire way. Thank you so much for all you do. As well, we are very excited for our upcoming speaker, Dr. Olav Lian. Will be joining us shortly. Dr. Lian was born in Vancouver, and after graduating from high school, he spent several years working while from time to time taking university courses. He really found what his direction, what he wanted to do, and became a full-time student and earned his bachelor in science in physics at Simon Fraser University. He joined the graduate program at SFU and completed his master's degree. He began teaching at UCFV in January in 2005 and currently holds a professorship in the Department of Geography and Earth Science at SFU. Thank you so much, and I'm so excited to welcome Dr. Olav Lian to the screen. Welcome. We're very glad to have you.
Okay, I'm trying to figure this out.
Yeah, no worries. We're all trying to
Share
figure
the
it out.
Screen. Make it
Perfect.
full.
I will let you take it from here.
Okay, thank you, Tiffany. Thanks for the introduction. I've got about 15 minutes to go through a lot of fun stuff, so I won't delay that anymore. What What I'm going to be talking about today is a little bit on what we do in the luminescence dating lab at University of Fraser Valley, where we use a technique called optical dating, sometimes called optical stimulated luminescence dating or OSL dating, to find out when the last time mineral grains have seen the sunlight. And why is this important? Well, this little cartoon, first of all, gives you an idea of how this works, and why it's important is it lets us get an idea about how stable environmentally sensitive landforms have been through their evolution over time, right? And that lets us say something about environmental change. So this method of dating sand grains was a Canadian invention. It was invented at SFU in the mid 1980s by David Huntley and colleagues. It was the first paper on it was published in 1985, and the year after that, I started working for David Huntley in his lab in the physics department. And I was a physics major, as Tiffany said, and I didn't know much about earth sciences until I started working on it in this lab. And I did get hooked on earth sciences there because the work that was being done by this professor at SFU was very much related to that field. And then I went on to do a master's in physical geography and then eventually a PhD in geology. So it all came together. But what got me hooked was this technique. And the way it works is that sand grains actually have little clocks inside of them, right? Believe it or not. It's a little more complicated, just call them a clock, but that's good enough for now. And those clocks can be reset when they're exposed to sunlight. If you take that little sand grain, right, and bury it in a riverbed, as is shown in this little cartoon in part B here. So now it's in the rivers here. The sand grains have been exposed to sunlight. It's in the ground. It's shielded from sunlight, right? The clock starts ticking again. It's the environmental radiation in the ground that drives the clock, right? If this river dries up, climate has changed, say in some part of the world, the river dries up and it becomes a dry sand bed and it stays like that for 1,000 years. And then somebody comes along and samples some of that sand, keeps it dark, takes it into a lab and measures it, right? The result will be an age that's 1,000 years old. And then you could say a river was flowing there 1,000 years ago. The little cartoon on the right, part C here, just shows the apparatus, a schematic of the apparatus we use. In the laboratory, we take the sand grains, put them on a little plate, then we shine light. If they're quartz grains, we shine green or blue light. They give light off of a different color, and we detect that light and measure it and analyze it and do some calculations on that, and then we get an age. So we're dating the last time sand grains were exposed to sunlight. And that is, like I said, it's a really powerful method to help understand how environmentally sensitive landforms have changed over time. So the best way to show you what the kind of research we do is to give 3 illustrative examples. And the work we've been done since the lab opened in 2007 has been all over the world, right? Right now we're working on projects in Tasmania, Australia, New Jersey in the US, and various other places. But I'll give 3 examples that are kind of contrast each other in time from close to home. So the first place I'll talk about is the Fraser River Valley in South Central British Columbia up here. And then I'll pop over to Savory Island that some of you may know about. It's a nice holiday spot on the west coast here. And then finally I'll jump over to Palliser Triangle, this dry area in the Canadian prairies where we've done a lot of work over the years. So the first example will be from Fraser River Valley. And any of you that have gone up into that area and done some off-roading or dirt roading, exploring around, maybe gone hunting or fishing up there, have seen these beautiful terraces in the semi-arid area of South Central BC. And it's a great place to work because it's so dry, at least down the valley bottoms, that you can see everything. There isn't big trees blocking the view. You can see these beautiful terraces on the west side of the Fraser River here that I pointed out with arrows. And they represent a time in the past, in the deep past, when this Fraser River was at different elevations. So You can imagine at the end of the last ice age, there was a lot of ice melting as climate was warming, environment was changing. These valleys like the Fraser, the Thompson, and the Nicola, and all the other valleys in British Columbia filled up with sediment. All that sediment being spewed out from the front of these melting glaciers was too much for the rivers to carry. So these valleys became almost completely full with sediment. And the Fraser River would have been flowing way up here where this arrow is at some time in the past, right? And behaving kind of like it does now. It floods, during the wet season, and you get sand being deposited on the banks, right? And then eventually it gets buried with more sand. And as the river was able to cut down into the landscape, as the ice age, the time of the ice age dwindled, became further in the past, it just stopped at various positions and left terraces behind. So we're working on this project to find out exactly when this happened and how it happened. And Travis Gingrich, UFV student that graduated in 2018, is now writing up his master's on this. He's the lead on this project. And here he is in a photograph on the right here, putting a sampling tube into an ancient riverbed to keep those sand grains dark. And he will collect those and take them to the lab and measure them, right? So he's done this in many, many sites in these terraces. All the work is done in the UFV luminescence dating lab. And I'm not going to spoil his surprise because we haven't published this yet. He hasn't defended his thesis, but I can say, that the ice age ended just before 12,000 years ago in this area, and the river started incising the landscape soon after that. And only a few thousand years ago did it reach kind of near the position that now. So this is really important for understand how the landscape of British Columbia adjusted to the end of the last ice age, to climate warming, and of course also to the evolution of the Fraser Delta, where Abbotsford is built on, or most of Abbotsford and Chilliwack and all the other communities down here, because the building material of the Fraser Delta is the sediment evacuated out as these rivers cut down into the glacial landscape. So that's a really interesting story that Travis is working on. Now we'll head over to Savory Island. This is what it looks like, right? Those of you who've been there recognize this. It's a beautiful holiday spot, lots of summer cabins and beautiful warm beaches. The South Beach is Hawaii of the South, I think they call it, because it's so, you actually get oysters living there. Beautiful place, but it's full of trees. Unlike the Fraser River Valley, where you can stand up high on a logging road and look down at beautiful terraces, what you see here is forest. We know this is a sandy island, which is very rare for the coast. Most of our islands are rocky, so this one is worth studying because sand is very interesting for us for obvious reasons. If you stand on the beach, on the South Beach here, I guess it's kind of over here, and look towards the shore, this is what it looks like. Bottom left photograph, very treey place, lots of big Douglas fir. And under there are the landforms we want to see, but we can't because the forest is there. So what we did was employed LiDAR, which is a really cool method. LiDAR stands for light detection and ranging. So we commissioned an aircraft that was actually out of Abbotsford here, and in the belly of it was a LiDAR camera that is owned by my colleague at University of Northern BC. And he flew back and forth across Savory Island here, shooting laser beams at the landscape. Some of the laser beams hit the ground and bounce back to the plane where there's a detector. Some bounce off of treetops and go back to the plane. Some bounce off a log in the forest. Some bounce off a bear walking by. It could be anything. But what you end up in, after a lot of laser beams pointing at the ground is what we call a point cloud. It's like a huge amount of data. And you can process that through computer programs and end up with what we call a bare earth image. So an image of the bare earth. So the computer strips away all the trees, and this is what you get. And these are false colors, of course. You just put in there by us for elevation. The red colors are higher elevation than the green and blue colors. But look at what we see right in the middle of the island here that you can't see from the satellite image, all of these beautiful sand dunes. If we zoom in on those sand dunes close up, they're beautiful things, right? These are the sort of things you might expect in a very dry area, like a desert, like a big desert in maybe North Africa or in the middle of the US somewhere, or in Australia. But here they are in the rainforest of British Columbia under a thick canopy of conifer trees. right? So this image on the right kind of shows how they would form in a very bare area with just a few shrubs and grasses where wind blowing off the ocean pushes sand from the beach inland, and these big parabolic dunes, as they're called, migrate inland. So these things on Seymour Island are quite long. You see the scale here is 0.5 kilometer, so some of them are 2 meters in length. And the little dots that are superimposed in there are just places we visited and we sampled for dating. And Libby Griffin, or Nee Griffin, now is Libby Bill, graduated from UFV with her Bachelor of Science in my department in 2014. And she took the lead on this for her master's at SFU, which she completed in 2017. And basically what we found out is these dunes started forming during a period of very dry climate in British Columbia, and they sort of ended during a transition to moist climate, right? So there's more to the story than just climate for these dunes to be alive and active. You need a good sand supply, a good wind direction. So we had a constant wind direction here, obviously, because they're so well lined up. But the climate might have been the big driver. So it's a shift, around 7,000 years or so to a drier climate that got, or from a drier climate, I should say, to one that got progressively cooler and moister, and to a point eventually when vegetation got in and anchored these guys and stopped that environment, and it turned from sort of a sandy, grassy area with big sand dunes to a big conifer forest. And again, we haven't published this yet. Libby's now teaching science at Abbotsford, which is great. She's such a great scientist. So we're working slowly on writing this up, but probably around 5,000 years or so, these dunes transition, or this field of dunes transition from a dune field to a big, huge state conifer forest, which is really interesting. So you might ask yourself, if climate shifts to being warmer and drier in the past, will it go back to looking like this? That's an interesting question. The last one I wanted, so we're getting closer to the present now in time. This is a really cool study. This is the prairie one. This was a project that was headed in the early 2010s by Stephen Wolfe, my colleague from the Geological Survey of Canada in Ottawa. And it was to do with the observations made by early explorers in what's called the Palliser Triangle in the prairies of Canada, right? It's this dry area. You saw my base map at the beginning here: Saskatoon, Regina, Medicine Hat, to give you some Calgary's over here to give you some context. And so this guy was commissioned by government in the 1850s, right, 1857, to explore this area to find out whether it might be a good place to settle. Could we establish an agriculture there, for example? So he went out there with horses and field assistants stuff, and in his diaries, what he reported on back then. So he published this in 1862 from his expedition, which went from 1857 to 1860. He talks about it like it's the Sahara Desert. The heat was very great while traveling through miles of burning sand. He talks about his horses, going thirsty and all sorts of things. And finally, he says, forever be comparatively useless for agriculture, right? And today, of course, it's one of our prime agriculture areas. It's a beautiful grassy area with all sorts of ranches and things, right? It's one of our breadbasket areas. And it's also interesting is that the tree ring record from this time period shows that the climate suffered from long dry spells. Okay, so that gives a hint that maybe Palliser wasn't giving a big fish story. That this place was actually appearing to him like a desert. In fact, he referred to it as the central desert of Canada. Right. So what we did was we went in there and we found sand dunes, right? And these sand dunes are under vegetation. They're stable, right? Not big vegetation like Seymour Island, but grasslands, right? And what we did was we dated those guys, and this is what they look like today. Right? If you look at just a satellite image from Google Earth, anybody can look at these cuspy things are sand dunes under beautiful green pastures. Here's the South Saskatchewan River. Medicine Hat's about 70 kilometers to the southwest there, to give you context. Right? So we went to some of these dunes and we collected samples and we dated them. And what we found out was that between about 1850 and 1934, the dunes are stabilizing. So about the time that that Palliser was there, the dunes had just started to stabilize, to become vegetated, right? But he would have seen that in his inception, and it's very likely that the way he described it was exactly right. In fact, the stabilization went on, at a slow pace till about 1934. And my colleague who headed up this project, Steve Wolf, found this beautiful aerial photograph from 1938 showing this area, oblique picture of an airplane. There's the South Saskatchewan River again, showing all these sand dunes here that are bare and mobile. The white areas is open sand. If you look at the same place from 2013, when we published the paper on this, you can see those bare sand areas are long gone and the areas become stable. Right, so our lab at UFV confirmed this, put numbers on it, put science to these observations by this early explorer that these sand dunes that were open and blowing around, like you could describe the areas of desert around this time, but soon after began stabilizing maybe as climate was getting moister and more susceptible to vegetation living there, and eventually today, of course, it's this beautiful agricultural area. Okay, so that's all I have time to talk about. 3 illustrative examples out of about 100 or 200 I could have chosen from that we've been working on in the lab over the last 15 years or so. I just want to end by saying, like, you can't do this work without extensive collaboration. You're working with biologists and geologists and geographers and people that are experts on coastal dunes, on inland dunes, and of course, lots of UFV students. So I'm just acknowledging a few of them here for these 3 specific projects. And of course, lots of funding from external agencies. UFV has been incredibly important in supporting my lab, but we couldn't survive in our research without several funding sources from the outside, which have been great over the years. Okay, that's my talk. I hope you enjoyed it.
Awesome. Thank you, Dr. Olav.
And now what do I do again, Jaws? I turn this off?
Yep, if you stop sharing your screen.
Okay, there we go.
There we go. Perfect. Wonderful. So before we continue on, just want to let the audience know, if you have any questions for Dr. Olav, now is the time to send them in the chat below, and we will start calling on them shortly. So Dr. Olav, I've got to start off by asking you, what got you into this field? What got you started?
Well, it was by accident. I was a senior undergraduate student in mid-1980s at SFU in physics, and I was taking a senior course in called Advanced Laboratory, just teaching how to work in a laboratory, essentially, in 4th-year course. And the professor that was teaching the course was the guy that invented this technique, and he'd invented it the year before, really, or within the last 2 years of me starting this course. And he asked me if I needed a summer job, right, as a research assistant in his lab. And at that time, I didn't know what he did for research. He was just one of my lecturers, and I thought, oh, I need a new car, so this will be great. I can start saving up for a new car. And then he said, I have to warn you. He might not remember this if he's listening, but he said, this discovery we've made is really interesting. I think it will catch on, and you may be doing this for the rest of your life. I just laughed. Yeah, right. And here I am, like 35 years or so later, giving a talk to you guys about it, and we're still pressing on and doing.
You must be able to afford a pretty nice car by now, hey?
Yeah. But with that experience, as a student, I didn't really know what I wanted to do, and I found something that was really interesting. That sort of changed my life. My career is what inspired me to establish it here at UFV, because I had a bigger lab like this in England at a university there before I came here, and the first thing I wanted to do was make sure our students got these opportunities that I had 35 years previously. I guess it was 25 years or 20 years previously at that point. But it's just so much fun to make little discoveries. It's just amazing, especially when you're an undergraduate and you make your first little discovery. May not change the world, it doesn't matter. It's just fun.
It looks like from the pictures that you've been able to provide quite a few of those experiences. Yeah, so I've got a question for you. What is the most drastic weather change that you've ever seen in your work?
Yeah, so weather and climate are two different things. Weather is this complicated thing that's hard to predict that you hear about on the 6 o'clock news, right? So if you monitor weather for a very long time, you can start talking about climate, right? So, that we don't work on the scale of climate. Our dating resolution doesn't work on that level. And also the landforms, probably a lot of them wouldn't respond fast enough. So that, that we're looking at longer term climate changes, changes that occurs over hundreds of years or thousands of years, and sometimes tens of thousands of years. So the most abrupt change in climate and in the resulting environment that we've had here in BC, for example, is the end of the last glaciation, the end of the last ice age, when we went from sort of a deep freeze into a relatively comfortable place. And the landscape just went crazy trying to adjust to that change. So this is, that first example I gave was was an example of that. So that's the most abrupt stuff. The last two examples were of more subtle changes in climate, and we're sometimes not sure why that happens. Why was it kind of wet and cold immediately following the last ice age, and then it became really warm and dry for a few thousand years, and then switched to moist and cool, and after that, right? And so it's so we know these episodes happened from what the biologists tell us from ancient plants and things and fossils they find that respond that way. So what me and my colleagues want to do is see, how does the landscape respond to those shifts in climate? So the Savory Island example is really abrupt, going from conifer rainforest to something that was bare, mostly bare open sand and giant sand dunes, 2 kilometers long, right? That's a big contrast of change.
Okay, and so island forests turning into deserts is pretty drastic. How you must have a really unique way of looking at the world. How has your work taught you to look at the world differently?
I mean, it's good and bad. And when I started my PhD at University of Western Ontario a long time ago, my supervisor there said, "You're going to start driving people crazy," because that's what he did. He said he goes on holidays with his wife and his 2 girls, and camping, and his wife would say, "Look at the beautiful landscape," and he would stop and say, "Well, I'll just let me tell you how that came to be," right? And then, well, you're spoiling the fun, right? So, if you know a lot and you've studied something for a long time, you can't, it's hard to sometimes just look at something for being beautiful, and you start getting frustrated. I got to figure out why it's like that, sort of thing. So it's sort of a curse. So so that it has changed my view that way, and but it also lets you filter through a lot of the garbage that you see in the news, the political stuff, especially sometimes from south of the border, where they're some of the things people are saying that are responsible for this or that is just completely wrong. And and that's why education is so important. Students need to be able to, people need to get educated and understand how things work, how the environment works, so they can filter through some of the stuff that you hear out there.
Totally. And it looks like a lot of your observations have been from the past, but do you also do statistical predictions about future changes at all?
No, I don't do that. There are others that do that. There's only so much I could do. I can barely keep up with this. The trick is, and it's also the fun part, is that we're so specialized now, and that's why I showed these teams of people on my last slide. I listed them there. A lot of projects require half a dozen scientists. I'm not just talking about the students that help us and learn from it, but you have people that are experts at soils or ancient soils. You have people that are expert at how sand dunes form, and then there are others that are experts at how to date the sand dunes. And then there are other people that look at fossil organic material that's buried in them, seeds and pollen grains, and can reconstruct climate for that. So it's hard to do everything. You have these days, if you go back 50 years, 100 years, there were people that did lots of things on their own, right? but that's very rare today. We become so specialized. So that, so that's the way it goes. So the people that forecast into the future are a different sort of animal for me completely. But our hope, people like me, our hope is that they will use our data to help make those predictions.
Okay. I've got another question for you. This one's from the audience. This one's from Joanne. What has been your most surprising finding over the years?
Oh my God. I'm going to have to take half an hour to think about that. So I've been doing this for well over 30 years now. Most surprising finding.
First one that comes to your mind.
Yeah, well, I mean, the first one that pops into my mind is that Savory Island one, right? It's to me, because I grew up in British Columbia, and I'm a child of the rainforest, right? And to be able to see those sort of desert-like features, those sort of, more arid type features that you don't really see anywhere in Canada right now, even in the drier areas, dunes of that size, perched on this coastal island off of BC. That surprised me, and I've lived and worked, in my profession in BC for my whole adult life, really. So I didn't know something like that existed until, about 10 years ago. It was a colleague of mine at SFU, a professor of the Earth Science Department, who had known about these and got me involved, but I'd never been to Savory Island. When he introduced me to the site, it just blew me away. And it wasn't until we saw that LiDAR, LiDAR is a relatively new technique, that laser scanning of the landscape. And when we got the results back, and I was nervous because we paid some good money to, to charter a plane and a pilot and have so when the results were emailed to me and I opened it up and I said, oh my God, it's amazing, right? Those sand dunes are beautiful. And they're hiding under that forest. Nobody can see them, right?
It's pretty incredible discovery.
And now we can see them. So that's pretty cool.
I've got another question for you. This one's from Gary.
Yeah.
How well does the optical dating process you use match the dates from other processes, such as carbon dating?
Yeah, so that's an incredibly important question. And the thing of, I didn't have time to go into the details of optical dating, but one of the major aspects of it is it's inherently experimental. So if you do radiocarbon dating, you can find a little seed or a little pine cone in an ancient deposit or a little piece of bone and send that to a commercial lab and get it dated. You pay them some money and you get it dated, and there are ways that can go wrong. There can be contamination and stuff, but the rest, they use essentially recipe driven now, unless it's a very complex or an unusual case, to get a good age, right? And it works quite well. And well, with my method, that you have to test it every time we go to a different site, because our what we date, the sand grains behave differently, not very much differently, but differently enough from site to site that we basically have to test the method again. So what we do is we try when we can to test it against other ages that are present that we believe may be more secure before we use them in another location at the same site where we don't have that security. So that's an important, and so what we do is, like in the first example I showed today up in the Fraser River Valley, we have volcanic ash beds in some of those samples where Travis is working, and we know the age of those very, very well. And so if we use my method to date those or bracket them with our ages, then we can fine tune our method and zero in on that age that we know. And then we can use that recipe that we create for that site, the laboratory protocol, on other sites where we don't have the volcanic ash layers, right? And because of all that experimentation we have to do each time and all the testing, it actually makes for a very good training exercise for students. We're not just giving them something or mailing something off to a lab in Ontario and getting a number back, or doing, sticking something into a machine and pressing a button and getting a number out. You go through a lot of experimentation to get an age or a set of ages. So any student like the two I showed here in the example, once they come out of doing all that, they've learned a lot about field work and a lot about laboratory work.
Okay. Wow. Yeah. Are you taking applications for more students right now?
Well, this thing called COVID happened, and so it could have messed us up for a year. We're actually working with 2 students right now, and after a lot of paperwork, risk and safety paperwork to keep it going, but not at our usual capacity. So once everything's clear again and we go back to normal, then we'll ramp things up a bit again.
Okay. I've got a question for you here. So you're referencing the sand dunes on the island. How do you know that they're sand dunes and not necessarily the result of flooding from waves or ancient earthquakes? Yeah, how do you come to those 2 conclusions?
So you're asking, how do I know it's the wind that produced those landforms and it wasn't away from the ocean, right? That's a good question, because we know the range of landforms that can produce using different processes, right? And that's called geomorphology, and there's people that their whole careers are based on that, and that's another reason for having this diverse set of colleagues working. And one of our colleagues on the Savory Island project is expert at dunes, and he cannot just say that these are dunes formed by wind, right? But he can say what was the strength of the wind that formed them. How much sand was blowing through there? What was the size of the sand? Because those dunes will change their shape, not just depending on, whether it's wind or not. They will change their shape depending on what the wind was like. How much sand was there? What was the anchoring vegetation like? So there's a whole series of sand dune shapes, and they each reflect a uniquely, well, not maybe uniquely, there's some overlap, but different environments, right? So an expert in that can tell a sand dune made by wind very easily from a sand dune made by water. They have different characteristics, right? So
Okay.
it's easy to tell them apart.
You mentioned that you don't peddle in the future of things as much, but when can someone expect to be able to go to a large sand dune in BC again?
Oh, well, that's what we're trying to piece together. We have. It's a big place. You said BC, you use BC there as an example. It's a huge province, and there are places we have not studied at all, right? And when I used to teach in England, they didn't believe that. I used to teach my senior students at the University of London, and I'd give examples from BC, and I say, there are valleys and plains and things you can study that if you want to go on and do a master's or PhD that nobody's ever worked at before. They just didn't believe me, because in England, every rock's been turned over almost, right? So what I'm trying to say is there's a lot of work to do here in Canada. We're a relatively young country with we don't have that history as some parts of Europe. So before we can make those sort of predictions, we need a lot more information. We need a lot more studies like this, right? There are changes that happen on different scales, right? So for example, the changes Libby's discovered on Savory Island cannot be extrapolated to other places in BC, or is there something unique about that part of the coast, that part of the coast, so that when climate shifted a bit, you got sand dunes there, right? Or it shifted a bit, you got forest. Well, that also worked further north, sort of thing. So and you get a feeling for that by doing more and more and more studies, and eventually we'll have a much better understanding on how the landscape of BC shifted together during one sort of regional climate shift, sort of thing.
It sounds like BC is a pretty exciting place to be and study. And
it is. It's amazing. We got alpine, we got coasts, we got a true desert in southern Okanagan. We've got it. It's a beautiful geological laboratory here to study all sorts of things.
That's great. I've got a question here from Shelley Canning, who's actually one of our next speakers at Science
I know
Talks.
Shelley well.
Yeah, she's asked, are we between glaciations?
Are we between glaciations? We sure are. So the last one kind of ended maybe 15,000 years ago. So we're sort of probably halfway in between, or maybe a little bit closer to the next one. So those large scale events can be predicted by astronomical events, right? So and they've been matched very, very well to those. So we can we're basically looking at the alignment of the orbits and the tilt of the planet, over time, and they change on cycles of 20,000, 40,000, 100,000 years. And when all these things combine in a certain way, we start getting cold, right? So those are the big global ice ages, right? Glaciations. So we can sort of predict probably within thousands of years, sort of when the next one will start to ramp up. But it's the smaller climate changes that happen in between that are harder to predict. And of course, we're forcing them as humans now. We're forcing them as well. So we're another variable, right, in it all.
Perfect. Thanks for speaking to that. So we've got a little while until we need to get our super thick jackets out.
Yeah, you got a ways.
I've got a question here from Paul. He's talking about a more local question. How were the sand dunes created on Old Sumas Lake?
The sand, so I don't know, because I've never studied the sand dunes at Old Sumas Lake, right? But if it's any open area, a wide open area that has a steady wind, right, and a source of sand will produce sand dunes of some sort. Yeah, right. So, so if there's a lot of vegetation, then that's a problem, because sand dunes don't form in big, huge, tall forests, right? But they can form and encroach in and move over vegetated areas that are grassy and shrubby and stuff like that, and maybe small forests. So
okay.
if there's a sand dune out there that's vegetated now, and which means it's stable in a fossil landform, that means that that sometime in the past it was more open, it was more sandy, it was, there's a steady wind source, and yeah.
Perfect. I've now got a question from Laura. She has asked, can you describe more details about how the clock in the sand grains work, and how you can measure dates from it?
Yeah. Oh, I could sure do that. I've given like 2-hour talks just on that in different places around the world. But basically, what we're dating are the most abundant minerals on the planet, right? So this is very fortunate. We're not looking for some rare mineral, right, that works as a clock. It's quartz we're using, which is the white sand you see on beaches, and then feldspar, especially the potassium-rich feldspar, which is the sort of salmon-colored minerals that you see in sand on the beaches, the sort of reddish. And there's other minerals we could use in principle, just that we understand how these behave very well, so we sort of stick with them. So so these minerals are crystals, right? They're crystalline structures, and but they're not perfect. There are impurities and defects in them, in their atomic structure, and these areas can serve as traps for electrons, right? So these are free electrons that are not bound to an atom. See, now you're regretting asking me, right? And these free electrons are produced when matter absorbs radiation from the environment. So the energy from these radioactive particles that are given off during decay of these radioactive elements interact with the atoms, strip off electrons, and they become free, and some of them can fill up these traps, right? So these traps are local areas you can think of as positive charge, and electrons have negative charge. So over time, these traps fill up. And some of them will hold electrons for just a few seconds, but others that we call deep traps, right? And there's several kinds in between. We can hold them for millions or billions of years, right? So those are the ones we're obviously interested in. Otherwise, we'd have a leaky clock, right? You hold that sand grain up to the sunlight, photons of sun, particles of sun, if you want to think of it, of light, would kick these electrons out of the traps, empty the clock, right? So we collect our sand from our sand dunes, say, keep it in the dark very carefully. And then we have special, very low lighting in our lab. For those of you can remember developing film in a photographic lab in the old days of film, that dim orange light you used in a photo lab, that's the same kind of light we use. So, and then what we do in the laboratory is we empty those electrons from their little traps in the crystal, and we count them. Right, the more there are, the older the sample is, or the more time has passed since the sample was exposed to sunlight. So that's the way it works.
So if there was, if somebody wanted to look further into maybe some of the work that you're doing, or that's taking place through UFV or some of the other organizations you're involved with, where could somebody go to find and access those?
Well, there's lots of publications out there, and some are more for a general science audience, right? So they're, and I've published some of those, right? You can even go to Wikipedia. There's a Wikipedia page on this, right, that explains it in a way that's probably accessible to most people. Even mentions that it was invented in SFU, so which is nice, right? And yeah, there's a lot of stuff written on it that you can find. So the technique's been around since the mid '80s, but there was an older technique that was around for much longer, that was sort of invented in the early 1960s, right? So that's sometimes mentioned as well. We don't use that technique very often anymore. We use the one from SFU. So this, and you look at my web page, which is embarrassingly out of date. I have a publication list there, and most of them are very technical papers, but some of them are review papers. A couple encyclopedia chapters I wrote a number of years ago. I think the last one was 2013 that explains the method. But probably start with Wikipedia. I've read that one, so I know it's good. 5 years ago I would have said stay away from Wikipedia, but it's getting a lot better, and it's almost peer reviewed now. And I'm a lot happier with it now than I used to be. So, and I've read the one for this method, and the article's pretty good. So that's a good place to start.
Oh, that's great. We're coming up on the end of our time here, but I wanted to be able to ask you, we're kind of in lockdown right now, but where are you just itching to get to once lockdown is cleared up? Is there a place that you just want to get to?
Yeah, I think most of us are itching to go someplace now.
With your work.
My sabbatical was sabotaged by the COVID, so I had planned to go to Reno, Nevada, because I had a postdoctoral fellow that was stationed at UFE then she became a research associate with me for several years. She runs her own lab there now, the Desert Research Institute. I was going to visit her for the first time, so that would be fun. That's more of a colleague visit thing. But as far as going to a place, we've been working on these amazing sand dunes and written a couple of papers on it already out of Tasmania, right? And I've never been to Tasmania. I just, my colleague in Tasmania collects the samples and sends them to me. I lived in New Zealand for several years, and so I got over to Australia. And I had a lab in New Zealand as well, like this one. And one of my former students there runs it now, which is nice. But I got over to Australia a lot, but I never got over to Tasmania. Now we happen to be working on sand dunes there, so I'd love to be able to go to Tasmania.
Perfect. So ticket to Australia.
In North Africa, my colleagues in the UK have done extensive work on, that have labs like mine. A colleague at Oxford University has a large version of my lab there, and he's done a lot of work in North Africa, amazing sand dunes there. So that would be fun to go see.
That sounds like quite the adventure. You're our local Indiana Jones.
I don't think so. Tickets all over the world. That's fun. We worked in Patagonia. We've worked in the Arctic and various places in the Arctic, and all sorts of neat places. U.S., Europe, Australia, New Zealand. You get around. That's the fun part about being a field scientist, is you go in the field, right?
Yeah. Wow.
And try to take as many students with you as you can. So. But yeah, it'd be fun to go to Tasmania.
If you need someone to help on the next one, let me know.
Okay, I will.
Yeah. Well, thank you, Dr. Olav, for joining us.
There's more questions. I can stick around. I'm not in a hurry.
Okay, perfect. I would like to let the audience know that, just as Dr. Olav has mentioned, if you want to chat your questions to him, he can see your questions come through and can type some answers as well. We'll link some resources to the email that goes out after our session today, along with the video of this recording. Yeah. But thank you again for being willing to come and join us here in this forum and joining Science Talks. And we're really grateful that you were able to speak to this.
No problem. Love talking about this stuff.
Yeah. Well, once you've gone for your sabbatical, you have to give us an update at Science Talks on what you found in Tasmania.
Yeah, well,
Yeah.
it'll be a summer field work because it's probably my last sabbatical now ever, right? The one I just finished. So I have to wait another 8 years for the next one, and I'll probably be retired before then. So it'll be something else I'm reporting on.
Well, we can't wait to see where your next adventure is.
Yeah.
Thank you for sharing with us today.
Okay, no problem.
Wonderful. I am now going to pivot to sharing my screen again for some closing remarks, but
Okay, so look, people who still want to do chat with me, maybe email me instead. Otherwise, I think it'll get a bit awkward if you do your thing, right? And then, so if you just sent me a chat that you want a message you want me to answer now, maybe send it to me by email and I'll answer it there. How does that sound, Josh?
perfect. Yeah. Oh, we've just put it. Looks like we've just put your email in the chat if anyone wants to send
Okay.
Dr. Olav some questions. Wonderful. Thank you.
Okay, well, thanks for having me.
No problem. Here, I'm just going to share my screen again.
Should I stop mine now? Okay.
Yes. Thank you. All right. So I'm just sharing my screen again. We want to thank our partners that help make this possible. Again, there's some community grants that we've been able to take advantage of using to help make Science Talks possible. We've also partnered with the University of the Fraser Valley. As you can see, there's been a lot of really exciting, groundbreaking research that's been taking place in our local area and with the University of Fraser Valley. We also have our local Abbotsford Tech District that really helps make these initiatives in our community possible, along with Connect, UFV Alumni Association, TEDx Abbotsford, the Abbotsford Community Foundation, the City of Abbotsford, and the Vancouver Foundation. So a lot of really cool local organizations helping to make today possible. This is not something that is done. That's just for tonight. We have many more exciting speakers to come. We do this every month, if this is your first time, with our next speaker, Dr. Shelley Canning, talking about ageism, the challenges of staying engaged and included. So join us on April 6th at 7:30 p.m. Again, there's going to be an email that goes out after this. You can register for all of the events at once through Zoom and get reminded about those as they come up. And we also have Dr. Satwinder Baines that will be joining us in May. So lots of exciting things on the books to come. If you want to check out Science Talks and more of what's coming and maybe past recordings, you can check out our website at sciencetalks.ca. And we are on a lot of places digitally. Feel free to email us, join us on our social channels, Facebook, Instagram, and YouTube, where these videos are hosted. We also are made possible due to the community. This is a community funded program, and it's to make science research more accessible to the community. If it's possible for you in your situation to donate and you like what you see, feel free to donate to this program on our website. We'd like to thank you all for joining us today. This concludes the end of our time together, but stay tuned and you will receive an email shortly. And don't forget to email Dr. Olav any questions you have. So thank you for joining us today in Science Talks, and I hope you have a great rest of your week.